So we've defined electric potential and we've looked at ways that we can visualize electric potential. Now we want to be able to calculate the electric potential in a variety of circumstances. These circumstances include finding the electric potential in a uniform electric field, finding the electric potential of a charged sphere, finding the electric potential of a single point charge, and finding the electric potential around multiple point charges. In this video, we're going to focus on the electric potential in a uniform electric field and finding the electric potential around a single point charge. We're going to deal with charged spheres and multiple charges in video 4. Now, recall that the relationship between the potential energy of a charge at a point in space and the electric potential at that point is UE equals QV. Now, rearranging this for electric potential, we get electric potential is equal to the electric potential energy divided by the charge. And we have to keep in mind that the charge in this case is the test charge that we're dealing with. Our general method for calculating the electric potential in each of these 4 circumstances is to first calculate the electric potential energy of a charge placed at that point, and then use this equation here to find the electric potential. So let's get started. We discussed uniform electric fields in Unit 5A, but a basic description is that they are electric fields of equal magnitude at all points within that field. We can easily generate a uniform electric field inside what is called a parallel plate capacitor, which is really just 2 parallel conducting plates upon which equal but opposite charges are placed. Finding the electric potential inside a parallel plate capacitor is equivalent to finding the potential for a uniform electric field, so we're going to use them as an example as we discuss this situation. Keep in mind, though, that what we talk about here applies to any uniform electric field, not just a field inside a parallel plate capacitor. Okay, so here we see a parallel plate capacitor. Notice that the electric field that's set up inside this capacitor points from the positive plate to the negative plate. That's the way it goes for all capacitors. Now, just like with gravitational potential energy, we're free to choose the point of zero electric potential energy anywhere that's convenient. So we'll say that UE equals 0 when a mobile charge is at the negative plate. The charge's potential energy at any other position then is equal to the amount of work done on the charge to move it at a constant velocity from the negative plate to that point. This is just like lifting a mass in a gravitational field. The work that is done to lift a mass at constant velocity is equal to the amount of gravitational potential energy that it gains. We have to say constant velocity here because if it's changing velocity, we would have to consider a change in kinetic energy as well, and we want to keep this as simple as possible. So we say constant velocity. Okay, so the 0 point of electric potential energy is the negative plate. Any work we do to move the charge away from the negative plate at constant velocity is equal to the amount of electric potential energy that it gains. Great. Now, in this picture, the electric field points to the left, so the force on the charge in that field is also to the left and is given to us by F equals QE, which we learned in Unit 5A. Since we're moving the charge with a constant velocity, the external force that we use must also be equal to F equals QE. This is the force that does work on the charge, changing the potential energy. So here's what we have. We have an expression for work. Work equals FD. We have an expression for the force on a charge in an electric field, which we solve for F, and plug into the work equation. So we get work equals QED. So the work done on this charge is equal to QED, where the Q is this charge. Okay, so the important point here so far is that we are moving this charge in this field, so we're doing work on the charge. We can find that work with work equals QED, but what is it that we know about work? We know that work is equal to the change in energy. The energy that is changing here is electric potential energy. So we can say that the electric potential energy is equal to QED because at our initial position, the electric potential energy is 0. So we can say that our electric potential energy is equal to the charge times the electric field times the distance moved in that field. But now you're thinking, hey, wait a minute. You said right at the beginning of this video that the electric potential energy is equal to this QV. Well, you're right, astute physics student. But remember how we rearranged that for finding electric potential and had the electric potential energy divided by Q. Now all we need to do is plug in our QED for the electric potential energy, and we get electric potential is equal to QED divided by Q. Just a quick look at this and we see that the Q, which is the charge we've placed in the field, or the test charge, cancels, and we end up with electric potential equals the electric field times the distance a charge has moved in that field. So this is the equation for finding the potential difference inside a uniform electric field. Now the V is the potential difference, E is the electric field, and D is the distance that a charge has been moved in that field. Notice though that we don't even need the charge to figure out the potential difference. This is because potential difference exists whether a charge is there to experience it or not. Uniform electric fields are set up in capacitors, so that is why we use an example of a capacitor to develop this. However, not all of the examples and practice problems that we will see use a capacitor. In many cases, you're going to simply be told that an electric field exists and some charge is being moved within it. You should also be aware that this equation is commonly rearranged into this form. So this is the equation that you'll have on your equation sheet for the AP test. Notice also that the electric field can be expressed in units of volts per meter as well as newtons per coulomb. Let's take a look at a real quick example. So two charged plates are 5 centimeters apart. The electric field between them is 775 newtons per coulomb. What is the potential difference between the plates, and what work is done moving an electron from one plate to another? So we want to know what the potential difference is between these two plates, and it doesn't matter that potential difference exists whether or not a charge is there to experience it, so we can just use V over D. Doing so gives us a potential difference of 38.8 volts. So now we want to know what work is done to move an electron from one plate to the other. Well, work is just a change in energy, right? And the type of energy that we're changing here is electric potential energy. Since we can set our negative plate as the 0 point for our electric potential energy, then the work that is done is simply equal to Q, the charge, times the potential difference. The charge on an electron is 1.6 times 10 to the negative 19. Our potential difference is our 38.8 volts. We end up with a 6.2 times 10 to the negative 18 joules of work done to move that electron. All right, so let's move on to looking at calculating the electric potential of a point charge. So now let's look at how to find the electric potential of a single fixed point charge that we'll call Q1. To do this, we'll again start by first finding the electric potential energy when a second charge is brought near, and then use V equals UE over Q to find the electric potential. We will call our second charge Q2. To begin, we need to calculate the work needed to bring Q2 from a point where the electric potential energy is 0 to some distance away from Q1. We'll call this distance R. Now we're free to choose the 0 point of electric potential energy at any point that's convenient. Because the influence of a point charge extends infinitely far, our result for the electric potential will have an especially simple form if we choose the electric potential energy to equal 0, and therefore the electric potential to be 0 at a point that is infinitely distant from Q1. In problems, this will often be stated as taking a charge from infinity to point P. It doesn't matter the distance from which we move that charge, because the R that we're going to be dealing with is the distance that our test charge Q2 is away from our fixed point charge Q1. Now also, we can't use the simple expression of work equals FD to find the work done in moving Q2 to point R, because this expression is only valid for a constant force, and as we know from Coulomb's law, the force on Q2 is going to get larger and larger as it approaches Q1. To do this calculation properly, then, requires the methods of calculus. However, we can understand qualitatively how the potential energy depends on the distance, r, between the two charges. Okay, so the figure here shows Q2 at two different distances from fixed charge Q1. When Q2 is far away, the force on it is small, so the work done on it is small, and the change in potential energy is small as well. This implies that the graph of the potential energy versus R is fairly flat when Q2 is far away from Q1. On the other hand, the force on Q2 is quite large when it gets near Q1, so the work required to move it through the same distance is much greater than before, and the change in electric potential energy is large, so the graph of potential energy versus R is steeper than when Q2 is near Q1. The general shape of the graph of electric potential energy must be as shown in this figure then. When Q2 is far from Q1, the potential energy is small. Potential energy must go to zero as R goes to infinity. As Q2 approaches Q1, the potential energy gets larger and larger. An exact calculation of this finds the potential energy of 2 point charges to be K times Q1 times Q2 over R. This 1 over 4 pi epsilon naught is the same as K. Look it up in your table of information on your equation sheet. Now, the graph used here is a graph of the potential energy for two like charges. They're both positive charges. But the equation is equally valid for opposite charges. In that case, product Q1 times Q2 will be negative. The potential energy of the two charges decreases as they get closer together, and a graph of the potential energy versus the distance r would be inverted. A particle speeds up as its potential energy decreases, which is true whether charges are alike or different, or whether we're talking about masses or whatever. A particle will speed up as its potential energy decreases. So charge Q2 accelerates toward that fixed charge Q1. The graph here shows, allows us to think about the attractive force between opposite charges from the perspective of energy. Example of this, take a look at example number 6 in your reading packet. Now, this equation, K times Q1, Q2 over R, gives the potential energy of a test charge, Q2, when it's a distance r from a fixed point charge, Q1. But we set out here to find the electric potential of a point charge, right? Well, we know that the electric potential is related to the potential energy by V equals UE over Q, where this Q is the test charge that we have been calling Q2. So, the electric potential of a fixed point charge Q1 is KQ over R. An analysis of these two equations shows that we simply solve V equals UE over Q for UE and substitute the result in for it. This results in Q2 canceling, which leaves us with this equation. Here, the Q is the fixed point charge that we've been calling Q1. Look on your equation sheet, you don't see Q1 and you don't see Q2 on all these equations that involve charges. It's going to be very important that you keep track of when a charge is the test charge and when it's a fixed charge in each equation where charges appear. Make sure then that you go back to each video, look in your reading packet, and verify which charge is which in each of these equations, okay? Doing so is it's gonna save you a lot of headaches and a lot of heartache. For an example of calculating the electric potential of a point charge then, take a look at example number 7 in your reading packet, and we'll do the same in class. We'll see you then.